Hello, welcome to video 45 in the lecture Advanced Mathematic Modeling. So in the last videos, for some time in the lecture we were discussing random walks in one dimension basically, and so we introduced this that the random walk is the sum of random numbers of the increments. And then we said, okay, we can make an analogy of this position x here as the position of a drunken man. So the drunken man goes randomly left and right or up and down, and then we obtain the profile of the random walk. But so far, this was just a kind of analogy, and of course we didn't expect to model the real position of an individual, of a human, by this kind of motion. But in fact, a random walk theory can be applied to the movement of living and non-living objects. And but in order to do this, we will firstly we will go to two-dimensional random walks, and that's really the topic of this video or the next videos. So to look for random walks in two dimensions and see how they can really be applied in movement ecology to describe the behavior, the movement of animals or organisms. And this all started with Brownian motion. So let's go like this. Okay. So probably you all have heard about Brownian motion. So Robert Brown he was a botanist, and he had 1827 he published this one observation that if we have microscopic observation if we take a grain of a pollen, so pollen of a flower, and we take a grain of the pollen, put it in water, and here we have a grain of pollen. Then this grain will not stay in its position, but it will make movement. It will make this kind of irregular movement in the water. And according to Robert Brown, this movement that we can see that this grain of pollen is doing, we call this the Brownian motion. And now there was a lot of controversy at this time. What causes this movement is this aspect of life. So is this pollen moving around? And so Brown did a lot of experiments, and then he could figure out, so no, actually this is not a manifestation of life, because if we took a non-living object, a dust particle, it takes the same kind of motion. And so microscopic observation, so we see the grain of pollen in water, makes a random irregular movement. But then at this time it was not really clear what could be the origin of this movement if it's not a living thing. So like, why should a pollen in water move around like this? And but then similar first here we have this observation, then similar observations were done with with different particles. Yeah, so like with dust particles. And so it was not clear what could cause this movement. And the theoretical explanation came much later. So this was your Brown. Theoretic explanation, and I'm not sure if you know about this. So that was one of the big deeds of Einstein. So Einstein, so this was 1905. One of his three major contributions was that he gave a theoretic explanation for this, and basically he introduced a random walk. So he said that's kind of a random walk. And another theoretic treatment was by Smoluchowski. A year later, this was 1906, and so basically probably we should attribute this theoretic explanation to both of these scientists. And so what was Einstein's idea? So Einstein's idea said, okay, if we have here this pollen, or we magnify this a lot, this pollen object, and which is moving around. Why could it be moving around? And then Einstein said, here we have the water molecules, and these water molecules, they make a random motion. So at this time there was already ideas about statistical mechanics, of kinetic theory of heat, and so there was a theory maybe a liquid as water is composed of many atoms or molecules which continuously move around and in this way have a temperature. But remember, at this time this was not really clear. It was just a conjecture. Nobody really knew if there are really such water molecules or gas molecules which move around randomly. And then Einstein said, okay, if these small molecules move around randomly, and they always will then collide with the pollen object, and by these collisions the pollen object would make some movement because he's just hit by small molecules. You get a small shift to the right and then shift upwards and so on. And so by this random encounters, collisions by the water molecules, we would see an effective motion. So Einstein then said we have a random walk. So a totally random movement of the pollen, and this is caused by collisions with the water, with the invisible water molecules. And so in some way the pollen is just of the right size. It's small enough that it can really be shifted around by the water molecules, but big enough that we can still see it here. So it's of the intermediate size, and so for the sake of this lecture here, this contribution of Einstein and Smoluchowski that created the random walk theory, and basically said like the movement of such an object in water makes a random walk. And this time, of course, I mean, this work by Einstein was seminal in a lot of aspects, but one of the most important is that it was kind of a proof that the liquid itself is comprised of small atoms or molecules which move around randomly. Maybe to continue the story, so basically now it was shown that the movement of these particles is not a living thing. It's also the movement of dust particles makes such a random walk. But the story didn't stop there. Then some years later, we have here the scientist Brownian, I have problems to pronounce the name, 1913, he made microscopic observations of real living particles. Microscopic and so he took very small living organisms, so he took protozoans, so that's unicellular organisms, protozoans, and so we will see, like when we now analyze here the movement of these objects, again we are interested in the mean square displacement, and Einstein was showing that, so basically the pollen is doing this diffusive behavior where the mean square displacement goes proportional to the square root of time, and or the mean square displacement goes proportional to time, and the mean distance goes with the square root of time. And then here Brownian, he analyzed now the movement of such unicellular organisms in water, and he found then also that we can describe this movement as random walks, and also the organisms, the mean square displacement in organisms goes proportional in time. So basically we can also take a random walk theory to describe living organisms. Theory to describe living organisms. And then the whole story didn't stop there. So nowadays we use random walk theory not only to describe microscopic particles, but also large animals and even humans. Yeah, so basically a lot of the material that I cover in this lecture basically started, or the theory of this started in the work of Einstein 100 years ago, or more than 100 years ago. And I will not follow the development of Einstein, but now we can now look for two-dimensional random walks. Obviously we now dealing with a walk in 2 dimensions, and we look at this in the language that we developed so far in this lecture. So we're looking for here a random walk in 2D. So, and then again we say we are interested in the position of walker, and the position is a vector, it's a 2-dimensional vector, and the position is changing as a function of time. And again, as before, we say this position is sum of increments, and the increments are now also vectors, and we sum from time 1 to time t. So basically the way we formalize the random walk is as before. The random walk is a position of random numbers, but now these random numbers are replaced by random vectors. And now, okay, so you see every increment here corresponds to a collision of a water molecule to the pollen, and so the position of the pollen after some time is the sum of small movements created by collisions. So random walk is again random walk is given as the sum of increments but now the increments are vectors. So the increments are vectors, which means we need to take here the vector sum into account. And then it's clear if we now have our spatial system. And now, of course, now it depends again, like what is the distribution and the correlation function of all these increments here. So, but basically, let's say the increments, but very often there could be just small steps to left, right, up and down, but it could be also like we have here a small increment E1, and we have another increment E2, and so on. Now the question is, do the increments all have the same length or not? So in general, the increments do not need to have the same length, so we can have long increments, small increments, and in this way we now obtain then the position. Maybe let's make some more, and then the position of the walker from the origin. Maybe we have started in the origin, and then the position. So let's make this red. So that's then the vector r of time t. It's the sum of all these random walks, and we start here in the point 0 in our coordinate system. And by this now you also see the new flavor that's coming into this, because the randomness of the trajectory over time now can come either that the absolute value of the increments is fluctuating, but secondly also that the direction of the increments can change in time. So we have now two flavors of randomness, two origins of the characteristics of the walk. Let's call it of the randomness that enters here. So we have random changes in the absolute values, of the increments, so the absolute values, and we have random changes in the directionality of the increments, and that's the new thing. So even if all increments have the same step length, just because the direction of every step can be arbitrary in this plane, effectively we can obtain a random walk. And so this we will explore in more detail in the next video. for the moment, I want to conclude here. I mean, this is of course not a full history of the theory of random walk. It's just like just 3 time steps to put the whole thing into context, so that at the time when the whole thing was evolved, the framework evolved, it was about movement of such pollen and waters at a time where we didn't even know if water molecules exist or not. And so there was a lot of guesswork needed, and so this random walk theory as we know it today was kind of needed to explain and resolve the puzzles of this kinetic theory of gases. Okay, so for the moment, thank you.